அந்த யூடியூப் லிங்க் மட்டும் அனுப்பிச்சு விடு.
இந்த 2 minutes அனுப்புறேன்.
அப்பா
ஓகே.
இந்த ஸ்கூல்ல ஸ்கிரீன் ஷேர் பண்ணும்போது the host all disable participation screen sharing.
இல்ல ரெண்டுமே ஒண்ணுதான்மா. இது ரெக்கார்ட் பண்ணாலும் நம்ம யூடியூப்ல உள்ளதான் ரெக்கார்ட் ஆகும். இதுல பண்றதுதான் பண்ணலாம், ஒன்றும் பிரச்சனை இல்லை. நான் வேணா பண்றாங்க, ஒன்னும் இஷ்யூஸ் இல்லை. இப்ப என்ன யார இப்ப ஸ்பீக்கர் வந்தாங்களா? ஃபர்ஸ்ட் ஸ்பீக்கர் கங்காதர், அவர் வந்துட்டாரான்னு தெரியல. ஆமா, ஃபர்ஸ்ட் அவர் வந்த பிறகு அவர் செக் பண்ணுவோம் எல்லாம். ஓகே, கங்காதர் வந்துட்டாரு நினைக்கிறேன்ப்பா. கங்காதர் வந்துட்டாரு, அவர் மட்டும் உள்ள. ஓகே ஓகே சரிம்மா. ஓகே ஓகே. ஹலோ சார், can you hear me? Mr. Gangadhar?
Hello, yes, I can hear you. Hello,
sir.
Can you hear me? Hello. Hello.
Hello, sir. Can you hear
Can you
me?
hear me?
Yeah, yes, sir. Yes, sir. Can you able to share the screen, sir? Can you check whether the system is able to share the screen?
Yes.
Can you try now? Because now no more participants, so we can just try it out whether everything is okay or not.
Yes. Says host disable participant screen sharing.
Then 1 second, sir. I'll do that.
Yeah.
Now check, sir.
Yes.
That's so good. Okay,
Yeah.
fine. Okay, sir, no problem. Just make a mute. Don't share the screen now.
Okay.
Do the welcome address, then we can just proceed with the same proceeding, sir. Thank you.
Okay.
Thanks, sir.
Thank you.
Hello.
Hello. Hello, Nirmal. Nirmal. Hello, Nirmal.
Yes, Manikandan. Can you give a few sentence like a test? Okay, check 1, 2, 3.
Yeah.
Give-
Could you hear me?
Yes,
Could you
yes,
hear me?
yes. I can hear it clearly.
Yeah. Thank you. Thank you so much.
Our speaker is here. Mr. Gangadhar is here. You can just welcome.
Yeah. 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 Let us start the session sharply by 5 o'clock. Okay.
Okay, no problem. Just another 6 minutes is there ready. So
Yeah.
maybe 2 minutes, almost 4:58. I will allow all the participants in. Then
Yeah.
I will
Sure. Sure.
exactly
Yeah.
by
Yeah.
5. Okay, thanks.
Yeah. Yeah. Thank you. Thank you.
Good evening to one and all. Today, I would like to welcome you all for the second day of International Virtual Symposium on Recent Advances in Chemistry, Chemical Science. Now, I would like to invite Dr. G. Manikandan to give an introduction speech about the speaker. Mr. Manikandan, the stage is yours.
Yeah, thank you, Nirmal. Thanks for your invitation. Yeah, dear fellow participant and the today's speaker, a very good evening to one and all. I extend my warm welcome to you all for the second day of International Virtual Symposium on Recent Advances in Chemical Sciences. Let me first introduce the speaker of session 3, Dr. Gangadhar, Assistant Professor and Lab Director, Temple University, USA. He did his PhD in the area of ultrasound-induced destruction of emerging contaminants. Actually, he developed ultrasound-based treatment technologies for removal of bisphenol A, 1,4-dioxane, perfluorinated compounds during his research work. And he has worked in various projects like analysis of microplastics in surface water, development of robust analytical methods for perfluorinated chemicals, antibiotics, and other organic chemicals. Removal of perfluorinated chemicals from water and wastewater using advanced oxidation process, groundwater remediation. So these are various projects he worked under these things, etc. Actually, he served as a graduate research assistant Villanova University during 2004 to 2006 and as a research assistant in Villanova Center for Environment during 2006 and 6 to 2008 and as a graduate research assistant in Temple University during 2008-2010. And he did his postdoc in Temple University itself during 2010 to 2014. And later he moved as a senior lab manager come adjunct professor in Temple University during 2014-19 and as assistant professor and lab director from 2019 onwards in Temple University, USA. And based on his research credits, he has a number of research articles and various awards and honors. I listed one by one. First place and overall research award by Pennsylvania Water Environment Association during 2009 and second place in Young Professional Fresh Ideas Research Award during 2008 and first place in Student Research Award by Society of Environmental Toxicology and Chemistry during 2007. And with this brief note, let me invite Dr. Gangadhar to take over the session. Thank you. Dr. Gangadhar.
Yes, good morning, actually good evening everyone, and thank you Dr. Manikandan for such a wonderful invitation and introduction. As Dr. Manikandan mentioned, I'm currently assistant professor in the College of Engineering at Temple University, and most of my research has been focused on water wastewater treatment and analytical method development. So today I'll give a brief overview of some of the research work and talk about emerging contaminants. Can I share my screen?
Yes, sir, you can share your screen. Thank you.
Yes, so today most of the talk will be focused on emerging contaminants. Okay, so a brief overview of the talk. Essentially, I'll talk about emerging contaminants are, particularly focusing on steroid hormones and bisphenol A, phthalates, and PFAS, a little bit on PFAS. And I'll try to tie in my research focus with all these chemicals. So basically, what are chemical contaminants? So chemical contamination or chemical contaminants, these are any chemicals that could be toxic to humans, plants, animals, and the contamination is generally used to indicate situations where chemicals are either present where they are not supposed to be. So if you look at industrialization period, there have been so many advances in science, and there has been huge development of various different types of chemicals. So since around 90s, many studies in the US have investigated how a lot of chemical compounds, industrial pollutants, human byproducts that have been making into the waterways. Because if you look at our water supplies and wastewater treatment technologies, so what happens here is you have a river, and upstream of the river you could have a wastewater treatment plant, and following a wastewater treatment plant you'll generally find a drinking water treatment plant. Followed by that, it will be a wastewater treatment. So it's a continuous process. So essentially, most of the drinking water treatment plants take river water or surface water. So it is very important we understand what types of chemicals are in those. So, and if you look at traditionally before looking at all these contamination and things, people were not really concerned about a lot of chemicals, because when they used to discharge these chemicals, they used to say, okay, these chemicals will be diluted. And the old mantra used to be dilution is the solution to pollution. However, that is not true, because sometimes these chemicals can bioaccumulate. So once any type of contaminants make it into rivers or streams, there are like studies that have showed significant quantities of these chemicals in rivers. And sometimes some chemicals could be hydrophobic, and they end up in underwater sediments. And many times the aquatic species that are in the water, they bring water, they are in the water. So sometimes these chemicals can bioaccumulate in those. And there are many situations, many studies that have showed migratory fish and that eat these insects, and even predatory wildlife that consume these different aquatic species have shown some chemical contamination in their bodies. Okay, so one example here where chemicals were discovered and some regulations came up. If you, I'm assuming most of you might have heard about lead. It was discovered, tetraethyl lead was discovered in 1854. This was used as a fuel additive. And later in 1904, there was health concerns where lead poisonings used to occur, and it was a concern. And 1965, it was detected in elevated concentrations in the environment. In 1970s, there was regulation on leaded gasoline. So mostly it's now unleaded gasoline. Some other chemicals, PCBs, TC, pesticides, they're all discovered at some point. They have been used for commercial production. They have been used in industrial products, and later time they have been discovered or associated with health concerns. And once they were started to be detected in the environment, regulations were placed on. And recently, it's PFAS. I'm assuming some of you might have heard about PFAS, these per or polyfluorinated chemicals, and these are currently a hot topic around the world. They are being detected at some locations very high concentration, some locations parts per trillion level concentrations, and there are some regulations that are evolving currently. Okay, so shifting towards contaminant, emerging contaminants. So we know there are chemical contaminants. Now, what are emerging contaminants? So these emerging contaminants could be anything that we use in our daily lives. For example, if we use like prescription medicine or prescription, non-prescription medicine, or personal hygiene products, or any kind of chemical additives, that we use and we dispose of. So these are currently associated with municipal wastewater treatment plants and the runoffs from agriculture. If you're looking into agriculture, we use pesticides, and there could be runoffs from that agriculture, and that pesticides can mix in our river waters. Or if we take municipal wastewater treatment plants, we could be using pharmaceuticals, and most of them don't, we don't use up 100% of those. So essentially, some of it is released into our municipal wastewater treatment plant, and those do not get treated. These treatment plants are not designed for that, so they can end up in their effluents. So essentially, emerging contaminants, we can say that these are any kind of chemicals that have not been previously detected, or those which have been found at very, very low concentrations. And currently, with technology, with improvement in technology, people are detecting these chemicals at much higher concentrations, and people are able to detect those chemicals in the water. So emerging contaminants, essentially, collectively, any kind of these newer contaminants that are showing up in our waterways, we can call them as emerging contaminants. Generally, they're also called contaminants of emerging contaminants, emerging concern. And they currently are representing a shift in most of the traditional thinking, because many industrial chemicals, many chemicals are produced industrially, but we use them and they get dispersed into the environment. So from our domestic use, not only industrial use, there are chemicals from domestic use too. And looking at this emerging contaminants is very important, because currently for most of these chemicals, the risk they pose to human health is not fully understood. There are some studies, which look at toxicity of some of these chemicals, and there have been reports that some of these chemicals could be cancer-causing, and all those at parts per trillion or nanogram per liter concentration. But although their actual risk to human health is completely not understood yet. Okay, so these type of newer chemicals that are recently getting detected are known as emerging contaminants. And there are several classes of emerging contaminants. We'll take a look at that later. So some of the prime examples are pharmaceuticals, personal care products, or endocrine disrupting compounds, and these are like steroid hormones. Sometimes if you look at farmers or people having cows and all those, they give steroid hormones to increase production of milk and all, and those can actually end up in our environment. Okay, so if you look at our oral drugs, almost only 10% of it gets used for its purpose, and almost 90% of the drugs, they pass through human body and essentially end up in our we flush them down the toilets, and they end up in our wastewater treatment plant, and they are not. The wastewater treatment plants really don't remove those chemicals, and they end up in our water supplies. So also, we use personal care products like soaps, cosmetics, fragrances, and many of them have found their way into our waterways. And I mentioned endocrine disrupting compounds or steroid hormones. These are substances that can actually interfere with the human hormones and functions of the hormones in the body. And trace amounts of these chemicals have been detected throughout the US. And if you look at US EPA, which is Environmental Protection Agency, they are working to improve the understanding of many of these emerging contaminants like what kind of toxic effects they could have on humans and aquatic life and all those kind of stuff. Okay, so and there are several studies looking at emerging contaminants. For example, this is a study from USGS. They have detected pharmaceuticals in many streams, even though some of these streams are not receiving wastewater treatment plant discharge. USGS, United States Geological Survey, these have found uh, a lot of pharmaceuticals, human use pharmaceuticals in streams. And from my experience, I am currently working on a project where we are looking at uh, some different types of pharmaceuticals, and we are going to one of the biggest river here, Delaware River, which supplies our water. It's a major source of drinking water in my locality, and it has a lot of streams associated with that. And we looked at like around 21 different pharmaceuticals, and we have been finding a lot of those in some of these streams. And those could be associated with, sometimes there are industries discharging without treatment. Sometimes it is human use. Sometimes people are throwing their drugs. All different types of things happen. And also there are other studies where pharmaceuticals have been found in groundwater, because some of these pharmaceuticals or estrogen hormones, these are hydrophobic. So essentially they tend to go into the sediments, and once they start going into the sediments, they start leaching into the groundwater. So there are some studies that show groundwater that has been contaminated with pharmaceuticals and hormones. Okay. And when we look at different classes of emerging contaminants, there are several of them. There are steroid hormones. These are endocrine disrupting compounds. There are pharmaceuticals, personal care products, pesticides, halogenated, non-halogenated compounds. There are fragrances, there are phthalates, bisphenol A, there are phytoestrogens, nanomaterials. There has been a lot of research going on currently with nanomaterials, but they do pose a risk, and people are looking at risk evaluation and all. And uh, the latest one is PFAS, which is per and polyfluorinated chemicals. So my research essentially focused on steroid hormones. I have done a lot of work on pharmaceuticals. Today I'll talk about steroid hormones a little bit, phthalates and bisphenol A and parent PFAS chemicals. So my research also included some pharmaceuticals, where we looked at several different types of pharmaceuticals in river water. Steroid hormones, I looked at several different matrices, and this was actually a part of my PhD study, where I used to go to all different kinds of municipal wastewater treatment plants and collect samples from their effluents and look at what kind of steroid hormones are released or essentially present in their effluents. So during that time, my research also focused on developing, robust analytical methods, because if we are saying that there are steroid hormones, we have to have like analytical methods for detecting those hormones. So my research was focused on that. So I'll go one by one and present briefly what I am working on. Before going there, let's look at how these enter the environment. So essentially, these emerging contaminants enter our environment every day, and that is from our modern lifestyle. So we use a lot of these chemicals in our lifestyle, and we buy a lot of chemical-based products. We use them, we dispose them. So if we look at manufacturing process, it could be pharmaceuticals or any other chemicals. They end up in some kind of a product that we personally use and effluents from our, and then dispose it off. So essentially, there could be, solid waste, there could be liquid waste, and all these things can end up in our wastewater treatments. Or pharmaceuticals can be used in hospitals or livestock, or sometimes there is some inappropriate disposal where people are just dumping them down the drain, or they are also used in aquaculture, many industries, and all these locations can end up releasing waste into our surface waters. And wastewater treatment plants, effluents, they are released into surface water. So essentially all the chemicals could end up in the surface water, and the surface water being one of the most important drinking water source here, and if we look at drinking water treatment technology, that is not designed to remove any kind of emerging contaminants. They are just essentially they remove turbidity and very very few viruses and all these stuff, but not really any kind of PFAS or phthalates or things like that. Okay. So these chemicals, once they're released, they remain in our wastewater and wastewater and beyond, because wastewater treatment plants are not designed to take these chemicals out. And similarly, not only our personal use, but industrial use. Many industries, before disposing of their industrial waste, they generally have their own treatment process. But from my experience, we have looked at several wastewater effluents from industries where, from manufacturing plants where they they produce high amounts of chemicals, and their effluents do have high amounts of those chemicals, and their treatment technologies are not able to remove all those chemicals, and they essentially end up they do not generally throw them in our surface water. They generally take their treated water, send it to municipal wastewater treatment plants, and those treatment plants treat them. But again, the story comes back to these municipal wastewater treatment plants, where they're only designed to remove BOD and certain organic compounds, but not really any of these emerging contaminants. So essentially, they all end up in lakes and rivers, and since these chemicals are getting into our environment, uh, and we are concerned because the health effects are not fully understood, and some we may have health effects. Sometimes they could be acutely toxic, and sometimes these contaminants have been detected in drinking water, and that is a risk for our human health. I have uh, read a lot of literature on steroid hormones in drinking water, PFAS in drinking water, and these are essentially cancer-causing, carcinogenic chemicals. So I'll switch gears a little bit, and I'll talk about all these different classes of emerging contaminants that I've worked on. So first one, my focus during my PhD was steroid hormones, and these chemicals are classified as endocrine disrupting substances, and they interfere with our reproductive systems, and they have been major concern worldwide because if they're interfering with our reproductive system or endocrine system, they can cause human problems. And these chemicals are known to be several thousand times more potent than many industrial chemicals. And one example is, there are some studies that showed feminization of fish. So, so when your wastewater has some synthetic estrogen hormones like 17 alpha ethinyl estradiol, which is a synthetic estrogen present at 0.1 nanograms per liter, that can convert male fish into female fish. So there were some studies where some people looked at fish species like upstream and downstream of wastewater treatment plants. So essentially, upstream of the wastewater treatment plant, the fish population was 50-50, like 50% male, 50% female. However, downstream, almost 98% of them, either showed all these male fish were converting into female fish because though that wastewater treatment plant was releasing synthetic estrogen hormones, and at 0.1 nanograms per liter, that's very toxic. Okay, nanograms per liter, parts per trillion. So again, if you look at the pathways of these estrogen hormones, essentially they are manufactured either for human use or animal use. And for human use, we use them and we excrete, and they are disposed, end up in POTWs, or publicly owned treatment works, essentially municipal wastewater treatment plants. And in terms of animal use, they're used animal farming. They can end up in soil, and some chemicals could be leaching out into groundwater. And from manufacturing, they have effluents too. Sometimes this effluent is pre-treated and released into wastewater treatment plants, or solid waste is generally sent to landfills. And all these systems essentially end up either in surface water or groundwater, and from there they can make their way into our drinking water or into the food chain. So essentially, starting from manufacturing, we are talking about all these entering into our we use them, and then they end up in our drinking water, or maybe in our cells. Okay, some examples. That's top one is the municipal wastewater treatment plant. And during my study, I have visited municipal wastewater treatment plants, collected effluents at several different processes, because wastewater goes through primary treatment, secondary treatment, and then final or tertiary treatment. So we have looked at how these chemicals flow through the system. I have also worked on some projects where we looked at how people dispose of their unused drugs, where some people properly dispose them, where they take them, give it back to pharmacies, say that we don't have a use, and they get properly disposed. But otherwise, there are many times we can just throw them in our trash and they end up in our landfills. Okay? And I have also looked at chicken manure and cow manure. We went to these chicken farms and animal farms, collected their manure because these are injected with steroid hormones, and looked at if there are any steroid hormones present in their manure, because all this manure gets is used for agriculture. So we have to see what's happening, what's the fate of these steroid hormones coming from any kind of these sources. So so there are two tables here. Top table is showing some of the concentrations of estrogen hormones in this is one of the study that I have already published. I am happy to share the link. So in this study, we looked at several different solid waste matrices, like municipal biosolids, poultry manure, cow manure, and mushroom compost. All these are used for agriculture. They are land applied for agriculture. So we look at some of the concentrations. We can see in municipal biosolids, we are talking about almost 1,000 nanograms per gram of 1,000 nanograms per gram of estrogen hormones in dry solids. And also in chicken manure, cow manure, and mushroom compost, we are talking about like anywhere from 30 to 200 nanograms per gram. And what we did is, because all these matrices essentially get applied to agriculture. So we designed a study where we looked at what happens or like how much estrogens generally dissolve from these matrices, because most of the estrogen compounds, they are hydrophobic. They stick to solid, but they also have capability to dissolve. So we looked at several different ways. We came up with a leaching study where we took each of these matrix, we kind of did a leaching study and looked at our effluent from that leaching, because that leachate is essentially what would end up in your groundwater. and there are studies showing these chemicals are present in groundwater. So when we look at municipal biosolids, the leaching study showed very low percentage, or only 0.4 percentage of estrogens getting dissolved. But when you look at poultry manure and cow manure, almost 27 to 35% of these estrogens are dissolving. And mushroom compost also showed very low dissolving, but these two could be of concern. Because there's a lot of dissolving, and that means that when these are land applied, they can end up in our groundwater. So now what we did is, we tried to estimate how much concentration could end up in a, could end up in your uh, surface waters or groundwater based on, maybe rain events or anything like that. And so for that, we looked at how much of these uh, solid waste is generated. So if you look at the US, almost 6.9 million tons of municipal biosolids are generated, almost 12 million tons of poultry manure, around 1,000 tons of cow manure, and there are around 15 million tons of swine manure. These are essentially a total of 1 trillion tons of solid waste is generated. And if we take the numbers that we have and multiply with these numbers, we are essentially talking about 76 tons of, these emerging contaminants or steroid hormones that could potentially be present in this waste. And all this being land applied, we are talking about uh, around 7,000 tons. I mean, if we look at the leaching percentage, uh, in terms of leaching, we are talking about 7,000 kilos of these estrogens that could be dissolved into groundwater. So, this is showing that, essentially we take all these polluted matrices, use them for agriculture, end up in so much high mass of steroid hormones present in groundwater. And this is in the entire US, not just any one location. This is in the entire US per year. So it's annual contribution. So, and this study is published here. I have the paper up here. I'm happy to share the link later if anybody would like. Okay, and so my other focus of my study during my PhD was to develop a treatment technology. So we know that there are these chemicals present in water. There are chemicals present in these emerging contaminants present in wastewater. So my study was also looking at advanced oxidation processes for removing these organic contaminants. And the technology that I worked specifically is ultrasound based. So we used ultrasound process, and ultrasound process is pretty very straightforward. You have to pass these ultrasound waves through liquid medium, and when you pass those waves, what happens is it creates something called cavitation bubbles. These are very tiny, but they are packed with like high amounts of energy. And if you look at some of the characteristics of these cavitation bubbles, they could be anywhere 10 to 200 microns in size, and they can last only like 2 to 10 microseconds. But in that, they can produce conditions almost similar to the sun, almost 5,000 degrees Kelvin and 1,000 atmospheric pressure. And these numbers are what drive the destruction of these estrogen hormones. And this study is published too down here. So what happens is when you pass these ultrasound waves, they pass like ray diffractions and compressions. And when these waves are passing, because of the compression and expansion, there is formation of bubble. And during a second compression season, cycle, essentially that bubble gets compressed and it packs all the energy in there. And when there's expansion, again it expands, and following, it goes on increasing, and at some point it reaches its critical size. So at that point, it essentially implodes or explodes. So if you take this one exploding bubble, we can represent it like that. So this bubble, there are 3 zones inside the bubble. There is inside of the cavitation bubble, there is an interface zone, which is this orange zone, and then the bulk phase. So if you look at the inside of the cavitation bubble, essentially this is where the temperatures can reach to 5,000 degrees. Actually, this is supposed to be Kelvin, 5,000 Kelvin, and 500 to 1,000 atmospheres of pressure. So if there is any water in there, if some of these chemicals are hydrophobic, they can essentially go from bulk phase into uh, this bubble, and because of the high temperature, there will be pyrolysis. Essentially, they break down. Or, water vapor can enter this cavitation bubble, and it produces these hydroxyl radicals. And these radicals can attack any kind of chemicals. So when it comes to interface zone, these radicals pass on to interface zone, and in the interface zone, destruction of any of these chemicals is due to radical oxidation. Inside the cavitation bubble, it's due to pyrolysis. Here, it's due to radical oxidation, and outside, because these bubbles don't last for a long time, they just last for 2 microseconds, and all those radicals get dispersed into your bulk, and in the bulk liquid, we can have radical oxidation, or sometimes, in the interface zone, we could sometimes have pyrolysis, but mostly it's radical oxidation. Outside in the bubble, in the water, it will be radical oxidation too. So essentially, this is how the ultrasound process works. And if we take this ultrasound process, it's even though it looks very simple, it's dependent on a lot of different parameters. There are process conditions, there are process variables. Process conditions could be like your sample pH or your wastewater pH. If we add any kind of additional oxidizing agents or anything like that, your water conditions. And the process variables are, what is your reactor geometry? How much power you're putting into the system? How much power intensity you're putting into the system? How much amplitude you're using? And all these variables, they are interdependent. So essentially, if you are changing the ultrasound amplitude, that can change the power. So in turn, it changes power density, changes power intensity, and that could essentially affect how much removal we can see. Okay. Yeah. So my study, we looked at several different variables. I have some graphs here. This first picture is showing effect of pH, like what can pH do, how can these estrogen hormones get removed. So you can see this. It's a little difficult to understand, but what I can say is, we were able to get higher removal rates for all the estrogen hormones at higher pH and at very low pH, and that is because of their pKa values and how they behave in the water. And then if you look at the amplitude, almost increasing amplitude, as we increased our amplitude of the ultrasound, we saw higher degradation. And also we looked at several different geometries, and you can see reactor geometry can have a significant influence where certain conditions gave us like very high removal. So essentially, we took all this and we optimized all the conditions, and we were able to achieve almost 90 to 95 to 100% removal within 10 minutes of sonication, and most of them, went close to non-detect levels around 30 minutes of treatment process. And during my study, I had a very good opportunity where I worked with Wyeth Pharmaceuticals, currently Pfizer Pharmaceuticals, and we actually installed a treatment plant at their manufacturing facility that makes these steroid hormones. So we were able to actually successfully install that, and currently it's under operation and removing some of these emerging contaminants that would have ended up in our waterways. So that's a little story on steroid hormones, and maybe as time permits, I'm going to talk about bisphenol A and phthalates. And uh, many of you might have heard about this bisphenol A. It's mostly, plastic, and it's a building block for plastic material. So phthalates and bisphenol A, and currently, if you look at water bottles, they say bisphenol A free or phthalate free, and all those kind of things. And you might have kids at your household, and we know they play with toys, right? So one of the projects that I worked on is looking at how infants and toddlers, they are exposed to these phthalates and bisphenol A at childcare facilities. So if you look at the US exposure to BPA is widespread, and it was estimated that almost 1 million pounds of BPA was released into the environment, every year. So it's very important that we understand the effects. And some of the US EPA studies and CDC, Center for Disease Control and Prevention, they found almost 90% of individuals aged 6 and above have detectable concentrations of BPA in their urine. And it is very important that we find out where it's coming from, right? So widespread exposure, it's generally it's concern for BPA because even though it's not a hormone, it behaves like a hormone. So BPA is something that exhibits hormonal properties. And there were studies where people reported development effects in newborns and fetuses, and when exposed to very low doses of BPA. And also phthalates, they are used as plasticizers and during the manufacturing process of these plastics, and they are essentially present with these plastics. And there are so essentially there are studies which showed these concentration of BPA, but the exposure route was not fully understood. There are some sources like maybe eating from plastic bottles, drinking from plastic bottles. Some could be, if you use plastic bowls and heat them up, and there could be BPA, but it's fully not understood. So one thing something that we try to look at is daycare, because essentially there are kids there, they constantly get exposed to these plastics, and we try to see if they are getting exposed to any kind of these chemicals. So what we did here is we went to a lot of daycare facilities, and we collected 15-20 toys from each daycare, and then we essentially took these toys from different rooms just to make sure that it's not biased study. And we developed wipe tests where we used to wipe them with certain type of wipes, which could essentially be the same as these kids licking on toys. So if you give a toy to an infant, essentially they put that in their mouth. So we tried to do that, and we wiped those toys, and we used to take those wipes back and analyze for BPA and phthalates. And to understand better, we better on how and where these BPA and phthalates are more, we try to correlate that with average income in the neighborhood. We try to correlate with cleaning technologies, like how the daycare facilities are cleaning all these toys at their facilities and all that kind of stuff. Okay, so I'll not go into all the details, but if you look at some of these numbers here, so the CF stands for child care facility. We do not want to expose their names, so we label them CF 1 to 14. And you can see the second column where I have the income range and the number of toys that we have tested, and we looked at all different chemicals, DHP, DBP, these are DNO, these are phthalates, and BPA is your bisphenol A. And you can look at some of the numbers here going all the way from 18 nanograms per centimeter square. So if you take one small square centimeter, we are seeing almost 18 nanograms of total BPA and phthalates going all the way up to 300 nanograms per centimeter square. So we were able to see a lot of chemicals that are getting released from just from these toys. And there's a lot more to do in this study, because it could be because of the age of the toy. If it's like an old toy, maybe there were no chemicals. Maybe all the phthalates have already leached out. If it's a new toy, maybe we are getting more chemicals. So it could be dependent on so many things. But essentially, one thing that we observed is most of the locations which are on the poorer side, poorer neighborhood, had like higher concentrations, except for this one location where they had been following certain daily procedures for cleaning their toys. Okay, so then we tried to correlate that to how much exposure kids could have. So what we did is we assumed that average body weight of infant would be around 10 kgs, and maybe they'll play with their toys for an hour. And when you lick them, they're not like, sometimes they lick the entire toy, they put the toys in their mouth and all, but we assumed just 4 square centimeters. And when you look at this, and this number is nanograms per kilogram body weight per day. So essentially, we are talking about pretty high numbers here. So almost all the facilities, we are talking a daily exposure. If you look at daycare 3, 2000 nanograms per kilogram of body weight per day. So that's a lot of exposure, and these numbers can actually tell us more on why people are seeing higher concentrations of these phthalates or bisphenol A phthalates in urine of adults or children. This was one of the missing trends where people were trying to find out exposure routes, and maybe this daycares or exposure to plastic could be one route. So essentially what I would say is what we saw is most of the leaching of these chemicals could be linked to washing procedures. And if you have toys, maybe clean toys using bleach and water around 3 times a week, and that's what actually resulted in lower leaching of chemicals. So more of this study, it's been published right up here. If I'd be happy to provide the link, but yeah, so even I have kids at home, and everybody has some kids, and their kids love plastic. Kids love toys, and they put them in their mouth. So it could be something like a take-home message where if you have toys, wash them, make sure they are not leaching chemicals. Okay, and also there are so many other things. We looked at manufacturing, where they came from, and depending on where their origin is from, origin country, that could have some impact on how much chemicals are leaching. Okay, so that's a little bit about BPA and phthalates. And then next class, I would go over a little bit would be per and polyfluorinated chemicals, and this is my current research topic. We are still working on development of treatment technologies, analytical methods, and all those stuff. But we're looking at PFAS in several different matrices and all that. So PFAS, per and polyfluorinated substances, these are again man-made chemicals, and they have been used in variety of industries around the globe since the 1940s. So essentially, PFOA and PFOS have been extensively studied chemicals among this PFAS group. And these chemicals are very persistent in the environment and also in the human body, and which means they don't break down. They can accumulate over time. So, and there is some evidence that exposure to PFAS can lead to human adverse human effects. So what are these perfluorinated compounds? These are compounds that have a fluorinated tail. You know, essentially that is like either hydrophobic or oleophobic end, and they have a spacer, and then there's a hydrophilic group. And this hydrophilic group could have, you know, anionic groups, carboxylic, sulfonic, phosphonic, all those kind of things. There could be cationic groups, non-ionic groups. So all these, you know, come under this per and polyfluoroalkyne substances. And there could be tons of them. There are around 3,000, 4,000 different types of these chemicals. So a little bit of history on these PFAS, you know, 86, you know, element, fluorine was isolated, and Henry Moissan, you know, actually got Nobel Prize in chemistry for that. And later, you know, during 1890s, there was chlorine-fluorine exchange reactions to prepare these aromatics. And 1931, GM is General Motors partnered with DuPont to produce, you know, Freon. And you know, there were some chemists working on these freons. They tried to chlorinate, but they accidentally detected PTFE. And you know, at some point, you know, 1953, there was this PFOS, something that's related to PTFE. You know, that fell on one of the chemist's shoe, and it left oil and water repellent coating. So that's when you know, water repellent stuff is born. And this PFAS, they are essentially used to make Teflon, or if you have these non-stick coatings and all those non-stick pans, they have all these chemicals. And later in the 60s, there were like firefighting foams that were developed, which are aqueous film forming. So essentially, when there is a fire, you know, this forms a film on the fire and blocks oxygen. So essentially works as a firefighting material. And late in 80s, you know, some studies found adverse effects. And actually in the 99, a farmer sued DuPont because they used to dispose of tons of this PFAS into local landfills. And that actually poisoned this water supply. And almost 80,000 people were drinking it. And some of these farmers' cows, the cattle, they mysteriously died. So essentially they sued. Then later on, you know, in 2000, they voluntarily halted the production of PFAS. And later in 2005, EPA concluded that this PFOA is likely human carcinogen. And then from there on, you know, there have been regulations growing on. 2009, they recommended 200 parts per trillion, or 200 nanograms per liter of PFAS, PFOA, PFOS. Again, later on in 2016, the number came down to 70 parts per trillion, that is 70 nanograms per liter in drinking water, combined PFOA, PFAS. And although, you know, there's a lot of regulations going on, you know, this PFAS chemicals are not manufactured in the US, but the problem is, you know, they could actually come from other places, because they are, you know, they're used in a lot of consumer goods like carpets, leathers, apparel, textiles, paper. If we are using any kind of like microwavable paper, microwavable like pizza boxes, non-stick pans, all those things have these PFOA coatings. Okay. So current regulations, some current guidelines, you know, New York is recommending 10 nanograms per liter. Vermont, they have 20 nanograms per liter. US EPA is still set at 70 nanograms per liter. And some of these states are looking at 5 nanograms per liter regulation levels. Okay, and also in Europe, they are suggesting 0.1 micrograms per liter, that's 100 nanograms per liter. or 500 micrograms per liter of all the PFAS in total. So there's a lot going on in terms of these PFAS chemicals. And where do we find them? We find them everywhere: food, commercial household products, workplace, drinking water, living organisms, because they persist and they build up over time. If you're looking at food packaging, essentially if you're looking at any kind of water repellent fabrics or non-stick products, polishes, waxes, paints, everything. Okay. And why are they important? Essentially, they are linked to all kinds of problems. You can see low infant birth weight, their effects on immune system, they're carcinogenic, they could be thyroid hormone disruption, they could have some effects on our human thyroids and all that kind of stuff. So I think it's almost 8:30. So my current focus is I'm working on analytical method development, and at Temple we use UPLC triple quad, which is a Waters Acuity UPLC ultra performance liquid chromatography with a ZeVo triple quad mass spectrometer to to analyze for these compounds. And we are also looking at ultrasound. And this ultrasound, this is not the same ultrasound as the previous one. That's a high power ultrasound. These PFAS chemicals, they can be removed using high frequency ultrasound. So there are different parameters. And also, my focus is on a lot of different AOPs. AOPs are advanced oxidation process, anything that has the capability to produce hydroxyl radicals, and these radicals can react with PFAS chemicals. So there are several different PFAS that are that I'm studying. There are like several small chain, long chain, sulfonic groups or carboxylic groups. So long chain sulfonic, long chain carboxylic, all these different PFAS, and that's my current focus, which we are working on. So that's a little bit about different types of emerging contaminants and my research focus. So essentially, I would like to acknowledge Dr. Raminda Suri is my department chair and my PhD advisor, and has given me an ample opportunity to work on this, and also the Water and Environmental Technology Center at Temple University, which has provided funding for all these studies, and several graduate and undergraduate students who have assisted me during that phase of all these different studies. So with that, thank you. And that's a picture where Temple University actually started. And if you have any questions, I would be happy to answer. Thank you all.
Yeah, thank you, Dr. Gangadhar, for your nice presentation. And now the session is open for discussion. So, dear participant, please introduce yourself and post your questions.
Well, Dr. Gangadhar Andaluri, Dr. Gangadhar Andaluri, good evening. This is Dr. Vivekanandan from AVC College, Mayiladurai. Yeah, you have very excellently narrated the effect of PFAS, steroid hormones, bisphenols, phthalates, etc. Now, basically, I have a question relating to this cattle, which are on the roadside, usually feed upon the posters, which may contain some toxic heavy metals like lead, cadmium, mercury, or titanium, or chromium, like that.
Yes.
And they also consume plastics in the form of polythene bags. Probably you may be aware that the veterinary doctors have recently taken nearly about 10 kg, 100 kg like that from the stomach of that particular cattle. Either it may be a sheep or that cow or buffalo. So they consume this pigmented inorganic species containing some heavy metals which are toxic, as well coupled with some organic, these so-called plastics in the form of these polythene bags. Now, similarly, the aquatic animals like whales, they also people have found, scientists have in the Discovery Channel, they have also shown most of in that particular stomach of that particular species, a lot of plastic waste. Again, these polythene bags are taken out. So, and also some oil spillage, crude oil spillage, which may contain BTX, etc., benzene, toluene, xylenes. Yeah. Well, yeah. I have basically a question relating to research, whether you have any comment relating to this, or you have done any work pertaining to accumulation of heavy metals in the stomach of cattle by way of consuming posters, and also taking some plastic bags, that is your so-called polythene bags, as well as these whales which contain in their stomach some these kind of plastic bags. I want some comments or suggestions or any results from your side on this particular environmental aspects area.
Yes, thank you for your question. Actually, that's a very interesting topic to work on. All these different chemical contaminants, because I have not particularly worked on these PFAS and any kind of animal issues or things, but I know somebody that have worked with fish that are in the streams, and they looked at how many PFAS and microplastics are in the fish tissue. So what they did is they just went to rivers. They collected like common fish, and they looked at PFAS in the river, and also they looked at PFAS in the fish, and they were finding like high concentrations of some of these toxic chemicals in fish tissue, which are they are bioaccumulating, and that could be true with these cattle or cow that could be consuming some of these papers which have inks and heavy metals or plastic. This plastic breakdown into microplastics. So currently I'm working on a project where we are looking at microplastics in rivers. So we are looking at tiny microplastic particles less than 1,000 micrometers in size, all the way up to 90 micrometers, to find out if there are any microplastic. And there is other group which is working on if these microplastics are accumulating in fish tissues, because if we are consuming the fish, obviously that's coming back to us, right? And there was one study long back in 2006 or 7. I actually helped an undergraduate student, actually a high school student, to look at what's coming in milk from these cows that are getting injections of steroid hormones. And what we saw was, there were significantly high concentrations of some of the synthetic steroid hormones in the milk, and those are mostly from these cattle farms where they inject them with steroid hormones to increase their weight or give more beef content and that kind of stuff, or produce more milk. And also we looked at some of the cows that were raised organically, where they are not fed with any kind of chemicals or papers or anything, and that milk did not have any synthetic estrogen hormones. So from at least what my experience is, even though I did not look at heavy metals, my research was never focused on heavy metals, but I have interacted with some groups that have worked on heavy metals in plants, where you use these manure or use kind of plants growing in landfills which have metals. They are taking up those metals, or PCBs. Those are found in plant tissues. From looking at that, these cows are chewing up on all these plastic material or paper material, they could end up in the milk. I did not do it, but my feeling is yes, could be there from at least the limited studies that I have read or interacted with some people on. So yeah, it could be a potential route to pollution.
You have also told that it's a PFAS, steroid hormones, bisphenol, phthalates are the endocrine disrupting compounds, name so-called EDCs,
Mm-hmm.
Fine. Then what about uh, these polythene bags as well as these heavy metals, whether they are going to affect in which way? You have told that these set of compounds are going to affect that endocrine glands, but relating to these particular inorganic species and in the plastics very beginning, that is these polythene bags, how they affect it? They are also endocrine disrupting compounds, or they act in a other way?
Microplastics generally they come under these PCBs or polychlorinated biphenyls, and these are linked to cancers. So most of the times, they could be carcinogenic chemicals, cancer causing, and they can also, if it has like BPA and stuff like that, or phthalates, they could act as endocrine disrupting, and they can weaken our immune system and cause reproductive problems.
Thank you, Dr.
Gangadhar.
Gangadhar, for your nice presentation. Hope everyone has enjoyed and acquired knowledge about how to manage the water resources and all. Thank you very much, Dr. Gangadhar. Thank you.
Thank you for inviting. I hope everybody enjoyed. And if anybody has any questions, you can reach out to me via email. My email is gangadhar@temple.edu. If you have any questions on the research or presentation.
Yeah, sure. I will send your mail ID to the participants too. Thank you so much. Thank you, Dr. Gangadhar.
Thank you.
Yeah, dear participants, let us move to the next session, the last session by Dr. S. Anbu. Anbu, are you there? Dr. Anbu?
Yeah, I'm here.
Yeah. Yeah, before going to start the session, let me take the opportunity to introduce Dr. Anbu, a well-known researcher in the field of MRI contrast agents. And he did his PhD in University of Madras. And to his credit, he served as CSIR SRF University of Madras during 2008-2010, and as a research associate in IISc during 2011, and as a Kothari PDF in IISc 2011 to 2012, and as a postdoc in Portugal during 2012 to 2015. And later he got European Commission Marie Curie grant, University of Birmingham, UK during 2015 to 17. And as a visiting researcher in IIT Kanpur during 2017, and as a STEM ambassador UK during 2016 to 18. And he got more awards like an outstanding reviewer award from elsewhere during 2017 to 18. And as a visiting researcher, University of Hull, UK during 2018-19. And he is a RSC Research Grant Fund, University of Hull, UK. And actually, he served to the society by conducting various awareness programs related to cancer diseases, especially to breast cancer. And actually, he's acted as a member in various professional bodies like the Royal Society of Chemistry, American Chemical Society, and Cancer Epigenetic Society, Royal Microscopic Society. And He acted as a reviewer in various reputed journals like Chemcom, RS Advances, Journal of Material Chemistry B, Inorganic Chemistry, Inorganic Chemical, etc. And for his research credentials, he's published a number of articles in reputed journals like Inorganic Chemical, Dalton Transactions, Inorganic Chemistry, etc. He also has some international research collaborations with the UK, Germany, Italy, Portugal, and India too. And currently, he is an independent researcher at the University of Hull, UK, and he is working in the field of smart magnetic resonance imaging probes for cancer imaging, funded by RSV Research Fund grant. Above all, yeah, he's a multiple personality too. He is a very good dancer. He knows Bharatam and native dance like Karagatam, etc. He's a multiple personality. He is personally known to him. Yeah, with this introduction, let me invite Dr. Anbu to take over the session. Thank you. Thank you, Anbu. Let us start the session.
Thank you very much, Dr. Manikandan. I'm privileged to be here, as particularly is a very traditional, is very well known and a traditional college, particularly the Kumbakonam Government Arts and Science College, known for good research, and many scientists are evolved from that department. So I'm very privileged to that department and other staff members and my friend Dr. Manikandan, including and the management and principal of that college. Thank you very much, and thank you very much for all on and off all. Just a good afternoon. Actually, here it's just in the 1:41. The time is around 10 past 1:30. Let me start just as my current science, what I'm doing in the magnetic resonance imaging. I would like to introduce this science since it is an underrepresented area of the research in India. So I would like to introduce some basic science, particularly basic physics and chemistry, particularly basic sciences behind magnetic resonance imaging. I would like to share my slides with you now. Just I think the people can see my slides, right? Can you say me any on? Is it okay?
Yes, sir, it's okay.
Yeah, thank you. Yeah, just let me start from this. Very good evening. Again, I am let me start from the basic science, because of the almost very few institutes only they are doing this magnetic the research on the magnetic resonance imaging, particularly developing contrast agents. I would like to I wanted to explore, I wanted to make you to understand what is meant by magnetic resonance imaging, how they are, what are the uses of the MRI, what are the sciences behind magnetic resonance imaging, and why we need to use the contrast agents. Then what is the use of the contrast agents, what is the chemistry behind the contrast agents, and everything will be discussed in these slides. So in the here in the title slide itself, I have shown some results. That is the compound I have developed, particularly manganese based contrast agent. This is the simple metal complex, this metal with the surrounded by some organic moieties. Simply we know that ligand, or we will say ligands. If the people are from Tamil medium or some other area, then you know that it is called upinical. It's otherwise known as ligands. Okay, so just I added the manganese is one of the biogenic metal here, and I have developed this kind of manganese complex. Then because of that magnetic nature of the manganese, I have used as a magnetic resonance contrast agent, imaging contrasting probe. Then we have achieved recently, we have achieved the in vivo profile. I mean, just we have injected in one of the healthy mice, and we got the very clear images of lung, liver, and kidney. So this compound will be very useful as a potential contrast agent to diagnose some disease or some abnormalities in the lung or liver or kidneys. So just let us see then from the core to fancier of MRI contrast agents. So we know that in Indian history, Susruta is the first surgeon of ancient India who was doing the surgery for his patients whenever some people approached with some abnormality, something is in their body. They wants to meet him, and they gets surgery by him. So and he was doing many surgery, and he was written all the methods and protocols about the surgeries, how to do and what are the organs present inside the body, and everything he has been written in the year of between, because of the we don't know exact time he lived in India, and also but the book is about in between the 600 to 1000 BC. So in his literature, particularly he has written, is called Susruta Samhita, is called Susruta's Compendium, is the most outstanding treatise of an Indian medical literature. Okay, so what we are getting this means just before this time, I mean before 1985, just maybe we will say is 1895. So there was no possibility to get diagnosed some abnormalities, whatever the abnormalities happening inside the body, without doing surgery or without cutting or opening the body. So it's not possible. So what happens in the year of 1895? It is just the Professor Roentgen discovered a new kind of rays which can penetrate only the soft tissues, which cannot penetrate the hard tissues, like which is made up of calcium phosphates or calcium salts. So that is nothing but, we know the calcium apatite is a calcium phosphates are nothing but calcium apatite. So it's mostly it's bones are made up of these kind of things. So this X-rays cannot penetrate the hard tissues like bones, but it can easily penetrate only the soft tissues. So because of this invention, then the people started to use to diagnose something, if maybe like a fracture or something is happening related to the bones, then easily we can identify. So this is the first imaging machine. It was discovered in the year of 1895 by Professor W. Roentgen. Okay, so after that, however, this is still it's a feel the people cannot use often, because it is this is the X-rays are is unknown rays, and also it's a highly ionizing radiation. Because of that ionization, we know that the before talk Dr. Gangadharan was explaining that it's producing some radicals, radical like materials, steroid materials are developing producing radicals, particularly oxygen rich species. So the X-rays can ionize, and also they produce some reactive oxygen intermediates and nitrogen intermediates, and also they'll mutate the cells, particularly the cancer cells. Some cells are highly vulnerable to get mutated. So such kind of cells are get mutated, and they are forming abnormal growth. I mean, there will be crores and crores or millions and millions of cells are developed within a short time of period. Okay, so in order to avoid this kind of discrepancies, or maybe these adverse effects of X-rays, so then the scientists start to think, yeah, other methods or other imaging modalities, other imaging modalities to in order to overcome this kind of very adverse problems. So just what they have discovered a new kind of method, that is magnetic resonance imaging. So this method is it is in the year of 1947. It's discovered by Felix Bolz and Edward Mills and Purcell. Then after that, it was run by, first time they were recorded in human. So they were using two kinds of sources which are harmless to the human body. So the one is magnetic energy or magnetic field, that is a very, very strong magnetic field. And also they have used radio frequency energy. The radio frequency, both the energies are very harmless to the body. So that is the reason it is became very excellent machine to diagnose the things without doing any surgery. So then we can identify what are the abnormalities inside the body. Or so this is the first image is taken by the Paul Lerterber and Peter Mansfield and Raymond Damadian, so who got Nobel Prize because of this invention. So now we will go to now we know that what are the energies they have used, how they are using. First we will see about some magnetic field. The magnetic field, we know that it is measured in Tesla, and a clinical MRI is performed in between. They are using, and clinically available MRI machines are running in between 1.5 to 3 Teslas. So it is around 50,000 times greater than the Earth's magnetic field, that is around 3 in 10 to the power of minus 5 Tesla. So this much of energy is enough to pick up a car. See, this is the symbolic representation of the taking car. That much amount of electric current is enough to pick up a car from a particular place. So that much magnetic field we are sending inside the body, and we are going to get the image. So now this magnetic field, it's all about completely about the magnetic field. So here it's all about strong magnetic field. This is the geomagnetic strength. It is around 2.5 to 6.5 into 10 to the power of minus 5 Tesla. So, but this is compared to the MRI machine, this is around 1.5 to 10 to 3 Tesla. So this is around 5,000 to 1,40,000 times stronger magnetic field than the Earth's magnetic field. So now we are surprised this much amount of magnetic field ever sending inside the body. It is very, 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 it's a very, very greater than the geomagnetic strength. So what will happen? Nothing will happen. So now we are going to get the very clear image. I mean, the inside the body, what is everything that's from the cellular level to we can get it. The images of the cells, from the cells to the major organs, even we can get an image by using this magnetic field. How? So the MRI scanner, this is the simple symbolic diagram of the MRI scanner. So there is, you know that, yeah, I think everyone we have seen that it is, the outer part is made up of is a very strong magnetic field. The inside there is the two kinds of coils. The one first coil is a gradient coil. The gradient means is just we are adjusting the radio frequency radiation. I mean, we are sending some pulses of radiation. I mean, a particular amount of with a particular seconds, the time course amount of sending the radiation to the body. That is why we are using the gradient coil. So this is the patient platform, and so this is the symbol, and we will come to know how it is working and everything. So MRI scanner uses the magnetism to see the position of water molecules. What we are measuring inside the body just is nothing but is a imaging water. Why we are choosing imaging the water? Why we are choosing imaging the water? Just applications. Just this MRI is allows to visualize soft tissues, including muscles, brain, lungs, and internal organs. Why? How this is visualizing these different organs easily means, so each muscles have a different amount of water. So water molecules are present in the body. So that only we are going to image. So then how we are going to image? So this is also this allowed to diagnose and evaluate disease progress, including cancer. It means we can easily diagnose the stages of the cancer. So particularly from the early stage to the later stage, and everything we can identify by using this MRI machine. That is a special advantages of this MRI applications. And another one is the medical imaging. So this is the one. So there are this cross-sectional and bisectional. You can see this from the cross-sectional from one head up to the one part to the other part. Here is from the top to bottom. So there we can cross-section easily. We can get what is happening, something inside. See here, there are some yellow and the dark red color spot. That spot is nothing but maybe some abnormalities in the brain. So we can easily identify by using the medical MRI without doing any. This is a non-invasive method. So just this is the other example. We know that is MRI brain images. So this is the normal 25-year-old adult's brain. So there is nothing we can find, but here is the normal athlete is age of 86. So because of that aging, the cognitive decline is, I mean, aging, it will cause some something like we will forget something like Alzheimer is a neurodegenerative diseases may occur. Where there are the lots of reasons are now is postulated. One among them is a deposition of the plaques, is a beta amyloid proteins, which is responsible for the formation of plaques. So because of the deformation of the protein plaques is causing Alzheimer diseases. And also we have to think of our memory power and our talking and everything is related to the hippocampal part of our brain. Why the hippocampal part? The hippocampal is an important part of the brain where there is, you can find the micromolar concentration of free zinc metal. I mean, free zinc ions are present in micromolar concentration level in the brain. So that is very important. That is why if maybe during the aging, if you are aging to the very elderly people, their amount, the concentration of the metal ions or concentration of the copper, concentration of the zinc, concentration of the other metal ions, particularly iron, aluminum, if maybe our accumulation of the some contaminants from the environments, for example, from the blood, whatever we are taking in the food. So these kind of materials can cause the deposition of this kind of Alzheimer proteins. So that will cause the neurodegenerative diseases, including Alzheimer. So we can easily identify, we can diagnose this kind of disease by using medical MRI techniques. So how does we are going to work? How does MRI works? So just it is working based on the NMR technique. I mean, many of us, I think we are from the chemistry department or otherwise. I think someone is please someone is disturbing me, and I think close your mic. I think that will be mute your mic, please. Just as based on the NMR technique, which allows to elucidate. We know that most of we are from the chemistry and some of the science students we are here. We know that we can use the NMR technique to elucidate the structure of particular organic compound or organic chemical. So how we are getting the structure or the physicochemical structure? Just we will see this NMR machine. This is the symbolic representation of the NMR machine, where there is a sample holder, is a small tube. So this is surrounded by the coil. That is, coil is nothing but radio frequency or radio wave coil. That both of these coils are surrounded by the strong magnet without any cooling jacket. Because of this magnetic energy, if we are sending the, we are producing the large, I mean, strong magnetic field. Because of that, it may convert, produce the convert the lots of heat energy will be released. So in order to control the magnet very control the magnetic release temperature, so we are using the like a helium cooled liquid nitrogen jackets around the strong magnetic field. Okay, now we will come to the point. So now we are taking any molecule, like one organic molecule. If you are taking any methanol or ethanol or whatever it may be, that organic compound we are taking here, we know that in the each organic molecule have the different functional groups or different aliphatic or aromatic region. According to their surrounding or according to their chemical environment, the proton can undergo resonance. They can in the because why the protons are resonating, or why the protons are magnetically active. We know that proton is the nothing but only is a nucleus, is with only positive charge, and also there is a neutron is also there, but the neutron is a chargeless, but proton is a charged, and also they spin their own axis. Because of that angular momentum and mass, they starts to spin on their own axis, and also they are magnetically active. So now this in the molecule containing protons can precise, or they can resonate in different frequencies. They according to their chemical environment. It means if maybe, for example, methanol CH3OH is OH is one hydrogen is there. So the hydrogen is attached to the oxygen, highly electronegative oxygen. So because of that highly electronegative atom environment, this proton resonate in particular position. That is nothing but chemical environmental shifting. So the same principle. Now we will then according to that, so they will absorb a particular amount of energy. Now I will how the protons are resonating, why they want to resonate. Just let me give you a good example. So just let me start from the one example. Just if you take a cup of water, if you take the cup of water, just you can now in the room temperature, you can touch, you can able to touch the water, because that is in the ground state, that is it is possess lower energy. So the same cup of water, just if you're keeping on the stove, just you are started to supply some amount of heat energy. After a few minutes it starts to boil. Now you can't touch. So now it is in the excited state, because it's absorbed the heat energy. So that energy after absorption, that if undergone to the excited state. The same then now if you're while you're stop the after just you stop the heat energy, then the water will come back to the original state. By absorbed energy will be released. The same principle just you can apply here. The proton will undergo resonate. They starts to spin on their own axis when you are in the applied magnetic field. So when the proton in the aligning or spinning along the external magnetic field is in the ground state. So when you want to make it to an excited state, means you want to supply some amount of energy. So where in order to make the water to excited state, you have supplied the water heat energy. Here in order to make the proton to excited state, so we want to supply radio frequency radiation. So that just we are supplying just radio frequency waves, so that energy is enough to excite the proton from the lower energy to the higher energy. So how this? So how the protons are excited state. So when they are coming back, they will release the same energy. So when they are releasing the energy, that will be, we are using the detector and amplifier, and we are converting into NMR proton, NMR spectrum. That spectrum is corresponds to the surrounding environment. The same principle we are applying the MRI. So the MRI means here, this is the MRI, where instead of the water molecule, instead of the organic molecule, we are keeping human body. So where there is a coil, the coil is, and also this is the strong magnetic field. So we know that in the whole body containing water molecules, that water molecules are containing protons are getting pre-sized, or they are started to spin around their own axis, or align with external magnetic field. In order to make them to excited state, just we are sending the radio frequency coil. So when they are passing the radio frequency radiations, then they starts to go opposite to the magnetic field. Then while you're stopping, I mean, I said already that we are using the gradient coil. So while you're stopping the pulse of radiation, then the proton will come back to the original state by losing the absorbed radio frequency radiation. That energy we are using the detector and amplifier instead of the conversion of spectrum, we are converting it to imaging. So that is called magnetic resonance imaging. So now we will see why we want to image the water. Just we will see that. So we know that how this earth is made up, 3/4 of the earth is made up of water. Similarly, our body is also made up of 70% of the body is made up of water. See, the different organs have different percent of the water. So different organs have different percent of water. So each the water content is differs. Now we know that each organs have different contents of water, and they have the different absorption or radio frequency absorption capability. So now we will come to this. We will consider only one water molecule. So just we know that is crores and crores of water molecules are present in our body. So we want to we are considering only one water molecule. So where there is a two hydrogen, one oxygen. Oxygen is magnetically inactive. Since it has a even number of electrons and protons, it will be cancelled. So just we will consider only proton. So the proton is a nucleus. So this proton, now we will the proton, just only one proton we will take it. So we know just we are considering one proton is a nuclear charge. So nucleus containing one proton. So this is the magnetized structure of the one proton. What happens? So just we are keeping in the it's running, it's spinning on their own axis due to their angular momentum and magnetic moment. So just we are keeping in the strong magnetic field. For example, around we are using 3 Tesla magnetic field. It starts to spin within a second around 63 crores. I mean, within only 1 second, the proton starts to spin very fast. It's unimaginable. It's that much fastly the proton is spinning per second. So then how do we can make them to excited state? I said already we have to send some amount of radio frequency radiation. What is the amount of radiation is needed to excite the proton? See, that is around 63.9 megahertz. That much amount. That's why we are using it is revolving or spinning around 63,000. 63 crores, that much times it's spinning. After passing the radio frequency radiation, the proton starts around an axis, around the main magnetic field, around the external magnetic field is called top. It's called, we know that already is nothing but is in most of the people are from Tamil Nadu, so I can say in Tamil is called Pambaram. How the final stage of the Pambaram, after running the Pambaram, so just at the final stage, it starts to run around their own axis. So that is called as a pre-seasonal frequency or alarmer frequency. That frequency will vary according to their environment, according to their physiological environment, particularly tissue environment. I mean, each water molecules in particular organ is the pre-seasonal frequency of particular organ containing water molecules are differ from the abnormal conditions. For example, if you consider the cancer tissues, maybe if you're comparing the pre-seasonal frequencies of the water in cancer tissues is differ from the normal tissues. That difference only we are converting into images. So the different pre-seasonal frequency or relaxation times we are going to convert as images. So what are the relaxations? Just that are two relaxations are majorly considered. One is T1 and T2 relaxations. So now we will come to here. So what is meant by T1 and T2 relaxations in MRI? It's a longitudinal T1 relaxations. The another one is a transverse relaxation. Longitudinal means if we are keeping the proton along the external magnetic field along the z-axis. I mean, just exactly the proton lying along the external magnetic field. Here the proton is around 90 degrees, mean perpendicular to the external magnetic field. So now just we are started to, I said already, in order to excite the proton. So we need to send some radio frequency radiation. So now the radio frequency, when you are sending the radio frequency, the proton starts to flip from around 90 or 180, or maybe opposite to the maybe flipping into 180 degree, the proton starts to oppose the external magnetic field. But just if you flip just 90 degree, that also is called flipping. So that also needs some amount of energy. That energy is getting from the radio frequency radiation. So I said is a water, in order to make the water to make it the water into higher energy state, we need to supply the heat energy. Similarly, in order to make the proton to excited state or flipped state or perpendicular or opposite to the magnetic field, means we need to spend some radio frequency radiation. Similarly, here in this, say already it was in the 180 degree or already it was in the perpendicular degree. So then what happens if you are turning on the radio frequency radiation, it starts to flip around 360 degree, then it will come back to the original state. So they are started to spin like this. It's like flip like this in the different angles around the x-axis. Now if you're turning off the radio frequency radiation, I said already, so while you're turning off, it will come back to the original state, that is along again it will come back to the z axis. So that if it's similarly, if you take here, it will come back to the original state. So the time needed from y-axis, from the 90 degree to the again to the original state, is called as the time needed to realign with z-axis in the magnetic field, is called as T1. I mean longitudinal or spin lattice relaxation. But if you see here, the proton is again it will flipped into around 360 degree, then it will be back after turning off the radio frequency radiation. So this is the same, the time is needed to flip around the xy axis around the in the perpendicular to the magnetic field, is nothing but T2, or otherwise spin relaxation or transverse or T2 relaxations. So now just we will see what is the use of the T1. See, this is the T1. This just is bisecting from the top to bottom of the body. So from that we will get this kind of images we can get it. So how we are getting? So the image, if you are doing this kind of things, the machines will cut numerous slides. I mean, like slices. I mean, if you, for example, if you take the mango, or if you are taking apple, if you're cutting into thousands of slices. So similarly, the magnetic, I mean, the MRI machine itself or computer itself, they are slicing from one part of our one ear to the other ear. They are making innumerous number of slides. So innumerable slides are because of these slides or combination of these slides, the cognitively, then we will get a single image, then where easily we can find where there is a defect and everything we can find it. And see, this is the T2 image, that is the cross sectional from the forehead to the back head. So here also we can get exactly where there is abnormalities, everything by using T2 weighted image. So these are the T1 and T2 weighted image. Now we come to the point, the chemistry is a contrast agent. Why we want to use the contrast agents? That is the very important question now. So we know that this is the figure. So where there is a flower, but we don't want this background, because this background, for example, this is considered as a cancerous cell. This is the normal cells. We need to find out only cancer cell without affecting the normal cells, means we need, because why we need to use the contrast agent? Because most of the time, both the normal and abnormal cells containing water, the pre-seasonal relaxation times and pre-seasonal frequencies are often subtle. I mean, they are very, very, very close. So we can't distinguish the normal and abnormal cells by without using the proton. That's why we are using some contrast agents. So in this place, we need some contrast agent. See here, so just we are using the contrast agent. So now we will get, in order to, we are the background we don't want, only we need this kind of image. So Just a good example with MRI, MRI without contrast agent. See here, nothing we can visible here. Just we will use one more thing. This is, see, this is the image with the contrast agent. So here you can find lots of some defects in the even the brain and other parts. So the gray matters are saying something is present, something abnormality is present in the particular human brain. So this is the use of contrast agents. So now we will go to the exact chemistry behind the contrast agent, because I said already the normal and abnormal tissues between the MRI imaging relaxation times. The relaxation times are often, they are frequently overlapping. So the abnormalities tissues cannot be diagnosed. That's why we are using shortcoming, this overcome by this problem, we are using contrast agents. So just I am giving you one contrast agent, that is called gadolinium contrast agent. What is meant by gadolinium? Why we are using the gadolinium? Gadolinium is one important lanthanide group of metals. So this is it possesses 7 unpaired electron in its outermost f orbital. Because of this large number of unpaired electrons, this metal is highly magnetically active. Because of this negative, more number of unpaired electrons in its outermost orbital, it can attract, electrostatically attract protons from the water. That is the reason we are using gadolinium metal, one of the main contrast agents. So here, this is then the brown color. This represented by inner sphere is nothing but this is the complex. I mean, free gadolinium should not be used. It means the gadolinium salt solution cannot be injected to our body. That is the main defect that causes a severe neurodegenerative diseases that will show in the later slides. So that is the reason we need to make it a very, very strong complex. Complex means the metal ion should be bound with a particular organic region that facilitate to penetrate the cells, particularly cell membranes. So here there is a water molecule. See here, the second sphere in the yellow sphere, there are water molecules, and third sphere is in the outer sphere, that is called solvent molecules, or in the water molecules in the tissues. So now here, the one water molecule is here. Just let us, just I am comparing with the Tirupati temple. I think we have been visited Tirupati temple, where in the main god, the statue is there. I think the Sankram, where after several hours we are waiting, just we will enter into the temple to see the god, but the people will be near to the door. They will not allow you. They will allow you for a few seconds, a few seconds, then they will ask us to go move out. They will say in Telugu is called jarugandi, like that. The same principle you can apply here. The gadolinium contrast agent is also working in the same way. It means it attracting, just it's coming, the water molecules, these are the water molecules, we are from the outside of the body or tissues. The water molecules are reaching the gadolinium metal ion, where this is the magnetically active metal ion. This makes the water molecule to get magnetized. Because of that chemical environment, the proton will get different frequency. They'll start to different pre-seasonal frequency. They'll absorb different amount of radio frequency radiation. So then when we are coming back to the original state, then it will release the absorbed energy, then we are going to convert as an image. So this is the basic principle of MRI contrast agents. So now we will, what is the exact effect? What is the effect of contrast agent on T1 relaxation? So we know that if the protons are lying along the external magnetic field, particularly Z axis. Now we are using the radio frequency radiation. Now it's flipping to the Y direction, maybe 90 degree. So now it is perpendicular to the external magnetic field, that is excited state. So now we are turning off the magnetic field in with two. Just we are comparing without contrast agent and with contrast agent. Without contrast agent, the proton, I mean, coming back very fastly to the Z axis. It's very, very fastly because the relaxation time is less. But here the contrast agent is coming very slowly. I indicated with many arrow marks. Here only I indicate only 3 arrow marks in between the x and z axis. So now this says that it's coming very slow. It means what? The protons, I mean the water molecules are resident time is longer. I mean they are near to the metal ion is very longer. They are very close to the metal ion, and they are getting strong magnetized when compared to these metals. So they will come to the original state very easily, but they will come very comparatively slowly. It will come back to the original state because due to the presence of contrast agent. So what is the image? So this is the longer T1. So this is the shorter T1. So what is the effect of this longer and shorter T1? So this is the fantastic graph that represents then what is the effect of the contrast agent. So here is a long contrast, a longer time. I mean without contrast agent, you say it's taking this is the without taking this, it's coming very fast. See here the brightness is only, I mean this is the without contrast agent, it's taking long. So now this is the brightness is, it is from the dark to the white. So the brightness is increases from here to here. So you can see only this reaches only the dark brightness is only here. But if you use the short, I mean contrast agent, see what happened. This is the without contrast agent. So this is with contrast agent. So now here nothing you can see in the tumor. There is a tumor is present, but you can't see because we are not using the contrast agent. But at the same time, if you're using the contrast agent, see here there is something a whiteness that is some abnormalities easily we can find by using the contrast agent. So the short short T1 means, so it's coming very fast. At the same time, the magnetization is very high when compared. The percentage of the magnetization is very high when compared to the contrast agent without contrast agent. This magnetization is very less. So this will this shows that the contrast agents are essential to make distinguish cancer cells, particularly cancer cells, to diagnose in the early stages itself. So now we will see the clinically available contrast agents. So many contrast agents are have been developed till this date. So particularly I'm showing only 4 of them. So that is OmniScan, Magnafist, ProHance, and Gado DTPA. So some of the structures I'm providing here in order to make you to understand. So these are the compounds. See, you can't see any gadolinium, free gadolinium. So everything is a complex state. The gadolinium is grabbed by the ligand. So it is present in the centrally, and also all the ligands are coordinated to the central metal ion. So there are one relationship between all these contrast agents is nothing but a coordinated water molecule. See here, this each complex possesses one water molecules. That is very essential or crucial for MRI contrast applications. So now what is the efficiency? What basis we are how we are identifying the efficiency of particular contrast agent? So see here, this is the only relaxivity is only 1 per second. It is around 3.8 millimolar amount of compound is getting magnetized. That is the relaxivity of this compound. It makes the only 3.8 millimolar complexes are getting magnetized. Similarly, if you're coming here, this 3.7, 3.5, 3.8, but here is 4.8 and 6.8. Why? Same metal, same it's a complex state. There are only one water molecules, but only the difference is in the outer and the same the molecular environment. I mean there is a different environment. This different environment means this full of aliphatic unities are present. This is the aromatic benzyl moiety is there. Here something phenyl, cyclohexyl diphenyl moiety is present. So because of this presence of this moiety, it makes the molecule to penetrate the cells easily. They will go inside the cellular membrane. They'll pass through the cellular bilayer, lipid bilayers, and they will go inside and will give the nice clearance. That's why they are the magnetization power also very high. So now we are getting a clear idea that so we need to make a very stable complex That is very important. Otherwise, if it is releasing free gadolinium ion, or if you are using the gadolinium metal ion itself, that will make you to severe diseases. Just we will see that just in one more thing, and that also I wanted to show you is now this is called smart or responsive MRI contrast agent. This is the next generation MRI. That is only I'm involving currently. My research is the development of smart MRI contrast agents. So this is the some reported in PNAS. It is recently reported contrast agents. So you see here, this is the gadolinium contrast agent. The both side, there is the inside there is some moiety with full of oxygens. This oxygen and nitrogens, this moiety is allowed to recognize only calcium. Understand? I mean, this part can bind only calcium. So this part can act as a magnetic, I mean, a MRI probe, and this part can act as a calcium responsive part. So what is the, why we want to, it should respond? So think about the neuronal functions. Many of the neuronal functions are depends upon the calcium channels. I mean, many neurotransmitters and everything there are the in brain functions are due to the calciums. So this allow to recognize the calcium ions wherever some organs have rich of calcium ions. So this molecule, if you are injecting inside the body, that can recognize the calcium ion where there is the calcium requirement. So they recognize the calcium and they'll show the enhanced image. Particularly, that's why they have shown the calcium response and they are acting as a chelator. But if you hear, so there are some gap. I mean, here it is very close to the calcium sensing receptor part. Here it is bit more longer than the gadolinium part. Just let us see what is happening there. So just this is the one calcium L2. So the L2 is showing almost there is no change upon addition of the calcium. It means it is too far from the magnetic MRI. So that relaxivity, there is no change. It means it's not acting as a responsive agent. But if you see here, the initially it was very, very less than, I mean, less than around 3 something millimolar per second. But if you're adding the calcium, that is relaxivity is increasing around 7.9. It is just, it will be indicated in the phantom images. So this is the compound without calcium. So with calcium, this is the without and with calcium. This both are same. I mean, nothing, there is no change. But here is a very highly contrast image we are getting. This suggests that the compound is acting as a both sensor at the same time. They are giving the enhanced imaging, enhanced MRI upon binding, selectively binding calcium. This kind of contrast agents are called as smart or responsive contrast agents. The same thing I am developing, the same concept I will in the later slides I'll show you. So now why we are going to manganese contrast? In recent days, all the researchers are developing, concentrated to develop manganese based contrast agents instead of the gadolinium based contrast agent. The reason, because sometimes some of the compounds are not stable in the biophysiological conditions. Till now, around 4 contrast agents are, I mean, they are stopped to selling, they are stopped to use for the diagnosis purpose. So particularly they are developing this kind of disease, particularly it's called NSF, it's called nephrogenic systemic fibrosis. I mean, they are settling inside the kidneys and other parts of the excretive systems. So that is gadolinium deposition disease. In order to overcome this, we are started to develop manganese based contrast agent. Manganese is one of the important metals of transition metal series, so which has 5 unpaired electrons in their outermost orbital. So because of this, gadolinium has 7 unpaired electrons, but manganese is a biogenic metal which is important for many biological functions, particularly cellular functions inside the cells. Particularly it's involving mitochondrial functions also. So because of that, that will be very grateful if you are using for biological systems. That's why we are chosen particularly manganese. We are in I'm involved in the development of manganese based contrast agent, particularly manganese based smart MRI for ATP. Let us see the later slides. So this is the compound I have developed recently. So this is soon it will be, we are already communicated to the one of the high quality journal. So we are expecting for the results. And this is the compound, the same moiety. This part is acting as a MRI probe. At the same time, this part here I am connecting with the two. It's called dipicolylamine. This dipicolylamine means is a very important ligand or well-known ligand for zinc binding. And also upon after binding of the zinc, it will leave two vacant sites, at least a few vacant sites for anion binding. So I have utilized, I have harnessed this excellent property of binding anions. I have made the manganese and zinc bound complex. So this complex, and I have titrated with a different phosphates, particularly because of this, both the zincs are in the close proximity, can bind the phosphates. So the upon binding of the phosphates, it can recognize the cancer cells, particularly breast cancers. I'll let you know then why I chosen the breast cancer. Now this it can selectively bind the, I have titrated with the different phosphates. See, different phosphates, it shows this phosphates, it bind with the phosphates, it's selectively, this compound shows selective binding of the ATP means adenosine triphosphate, which is it's very important material for the growth of the breast cancer cells. So if I inject my compound inside the body, so that can selectively recognize only phosphate, so then it will show the enhanced image of the breast cancer cells. Then it will allow to diagnose the breast cancer cells in the early stage itself, particularly the early onset of cancer. So now just I have checked with the different metals with in the different particularly I have titrated with zinc. That is, I you know that I already said, in the brain, in the body, there are more than high concentration of the zinc metal ion is present in the body. So if you are saying after injection, if the metal ion is releasing the metal, maybe manganese, if it is coming out from the complex, then that will be dangerous. So I said already, the gadolinium is also a free gadolinium is also a danger to our health, body. Or similarly, the manganese, free manganese ions also toxic, it produce some toxic effects. In order to avoid that, we are checked with some gadolinium for over 60 days. It shows that very stable, almost same fluctuations we are getting. So this suggests that the compound is, my compound is highly stable. So we were pH dependent, inside the cells, the mitochondria has different pH, and also blood has different pH. So in our body itself, there are the different pH conditions maintained in different organs. So according to that, we have checked with the different pH conditions in physiological conditions. The compounds are around from 5.3 to 10.3. It's 10.2 is around stable. It's I mean the laxity is stable, suggests that this is suitable to use in physiological conditions. So now I said already, this is selectively binding with different, I have used titrated with the different phosphates. So this is the relaxivity. This is the compound is selective with the ATP. It's binding in such a way. This is the binding mechanisms. And also this is the titrations. This is the routine titration method. It's highly selective to the ATP over other phosphate ions. And this is the relaxometry data. This is the phantom images. See here, the ATP bound system is around 10.86 per millimolar per second when compared to the dipicolyl or zinc moiety free complex, that is the MNLME. So that is the so this is number one is the manganese. This is currently available, I mean clinically available wherever the people are, mostly they are injecting during the MRI scanning. So when compared to that, this is showing excellent brightness when compared to this. This is the water samples. This is the other molecule, water molecules, other phosphates are zinc and phosphate free molecules also. So this suggests that the compound is highly selective towards ATP. So now we will come to the phantom images of only one compound. I told this DPA free is a free only MNLME. This is the phantom image suggests that it's increasing the concentration. This brightness is also increasing. This is taken by MRI imaging in University of Tübingen in Germany. So this is done by done by Italy, is one of the familiar professor, Professor Maroboto. So we were doing this dispersion, NMR dispersion analysis. So where it suggests that is a very longer, I mean, if we are from the lower frequency to the higher Larmor frequencies, the compound is not dispersed, only it's beyond 1.5, it is dispersing. It suggests that the compound is very high stable at all the range of megahertz. I mean, from the 0.01 to around 10 megahertz. Now, just this, we know that after taking any tablet or something, whatever, if you, for example, if you feel fever or something, like if something is happening inside the body or something, we are not feeling good, so just we used to take some pills. The pills, what is happening after taking that, it should go to the a particular abnormal part or abnormal area, so by through the blood. So in the blood, where it is going, the blood containing serum protein, it should bind with the serum protein. So we have studied with the different serum protein in the blood. As particularly, I have used the bovine serum albumin, and this compound shows excellent binding, and also upon binding, it shows excellent binding profile. So the relaxivity is increases, and this is the NMRD. So this is without BSCA, and this is the with BSCA, and this is the binding constant, this is the relaxivity. This is without BSCA is around 5.7, and with BSCA is to around 21.1 per millimolar per second. It suggests that this compound is strongly bind with the BSCA, and it will take to the all parts of the body through the blood. That's why it's called, suggested as a blood pool agent, blood pool contrast agent. So all parts of the body, it can easily, it will go. So now this is the routine experiment to find out whether the compound is binding or not, and that I have used this fluorescent titration method, and we found the contrast agent constant, that it is highly consistent with the previous experiment, that is a relaxivity experiment, the KD value. And this is the binding, some modified binding Stern-Balmer plot. Now, biodistribution of MNLME. So this is the finally we got this in vivo profile by using rat, this healthy rat, and we have injected, and we got a very clear difference between that. This is the difference between this pre-contrast and post-contrast. So this is the merged one. So we are getting these kind of, this is the heat maps suggest that there is a the compound is showing enhanced MRI. MRI. So this is the some compared with the clinically available contrast agents. So that contrast agent suggests that it is equally showing that high contrasting capability with the magnetic Magnavist, that is currently clinically available contrast agent, particularly gadolinium contrast agents. So now the summary is we have developed a new class of contrast agent, and particularly ATP responsive and free complexes. And we know that what is meant by MRI, and what are the chemistry and physics behind the relaxivity and contrast agent, why we want to use the contrast agents, what are the advantages, and everything we have discussed, and my research, and these are my research collaborations. So this is the University of Hull where I am working currently. So this is my mentor, but now he is moved to King's College London, St. Thomas Hospital, where I think that recently, because of the COVID-19, our UK Prime Minister was admitted in this hospital. He was working in that institute as a molecular imaging lecturer. And Dr. Lawrence, this is the government hospital from where I'm living. That's called Hull Royal Infirmary Hospital, is Hull. So where I'm doing the collaboration work. So this is one of the other collaborator, Dr. Andre F. Martin from the Germany, who is doing for all the in vivo MRI studies. And this is Professor Morabato from University Piemonte Orientale Avogadro from Italy. He is also helping for the NMRD studies. He is a familiar European scientist who is involving in the MRI research. So this is the paper. Recently, we were communicated to the one important high quality science paper, then soon I'm expecting the positive results from that. And acknowledgements. So I'm very thankful that I done my PhD in University of Madras. Then after that, I NIT Calicut as a lecturer for around a semester. Then I got a Kothari fellowship with Professor P.S. Mukherjee in IPC department and IAC. Then I got FCT fellowship, that also my own project. Then I was awarded this FCT postdoctoral fellowship. Then I gone to Professor Pombero, who is a well-known electrochemical and a catalysis scientist. So then I was only the person who started the bioinorganic research in his group. Then I got a Marie Curie award from the European Commission, and I moved to Dr. Anna Peacock Lab with the University of Birmingham. So then after that, I moved to Graham's lab. That recently I shown his picture in the Royal Society Grand Fund. Then recently I got PDRA position with Dr. Andrew Bowa's group. I am developing fatty acid metabolites. Particularly, I'm preparing the fatty acids from the seeds, particularly the plant seeds that will allow to cure the neurodegenerative diseases, including Alzheimer diseases. I'm very thankful to my all the funders for who supporting me for to coming to up to this level. So from the CSIR India and UGC Kothari Fellowship and FCT Fellowship from Portugal and Marie Curie Slowacka Curie Actions for European Commission and Newton Baba Fund from the Royal Society of Chemistry. Thanks for your attention.
Yeah, thank you, Dr. Anbhav. Now the session is open for discussion. Dear participant, if you have any queries, please introduce yourself and put up your questions.
Dr. Anbu, hello, good evening.
Yeah,
this is Dr. Vivekanandan from AVC College, Mayiladuthurai. Actually, what is the NMR frequency usually employed for this kind of diagnosis of patients, usually that particular spectrometer? What is the NMR frequency?
So radio frequency to be used is around normally is 1.5 is the maximum. Sometimes they are in order to very rare cases they are using higher energy like 3 Tesla. So normally is our human body itself can capable to get only 50 millimegahertz only. It's not beyond that. But however, so if you are applying the longer time, it may be more than 1 hour or 2 hours, if you are exposed with the magnetic field, strong magnetic field like 3 Tesla like that, so nothing will happen, but only except a few problems like dizziness and some like metal taste in the metal taste, this kind of only negative effects, but these are very temporary. So that will be gone within few minutes or 10 minutes or 1 hour. I think the harm, it is not harmful that much.
But usually in the laboratory of institutions of very repute like IISER, Indian Institute of Science Education and Research, or Indian Institute of Science, I hope now recently 900 megahertz, I don't know exactly right now, in which way the instruments available in the hospitals are different from the laboratories for the analysis of research samples and in that hospitals, with the top hospitals.
Sir, hospitals are completely is different from the NMR machines. The NMR machines are, it's a very high for energies we are using. I mean, 500 megahertz we are using. It's maybe it's not only for maybe it is in the clinically available instruments we are using very less. I mean 10 megahertz, like between the 10 to 15 megahertz only we are using. We are not using that much. It's like NMR machines where we are using that is 1,000 times higher than that. So it's a very different.
And also, why patients are those who are having some metal plates inside their body, particularly in the skull or in the knee, or they are having any metal plates, they are not at all allowed. I think it is not possible to examine using this MRI. Can you comment on this?
Yeah, that is true. The reason because if they have something like some heart, there's some places they are, if they're using those kind of materials, that is they are based on made up of metal, means that will make some magnetical attractive, because of we are sending that around 50,000 times is stronger magnetic field we are sending inside the body. So that may harmful, and also that may affect the metal plates, the whatever they were used for the some like a bone fracture or whatever it may be. That is the problem, I think.
Thank you, Dr. Anbu.
Thank you, sir.
Yeah, thank you, Professor. If you have any further questions. Yeah, if there is no further questions, let me thank Dr. Anbu for his nice presentations, and it is very highly informative to the audience. I hope so. Yeah, dear participants, now we are come to the end of this session. Yeah, it is the time to say vote of thanks. Yeah, thank you is the best prayer that anyone could say. Thankfulness is the beginning of gratitude. Showing gratitude is one of the simplest and most powerful things humans can do for each other. Yes, it is the time to show my gratitude who are all began me to make this international symposium a grand success. On behalf of the Department of Chemistry, PG and Research Department, I'd like to thank our principal, Dr. R. Rajendran, for giving us an opportunity to organize this international virtual symposium on recent advances in chemical sciences and extending his support towards the success of this program. I'd like to extend my warm thanks to all the speakers, especially to Dr. V. Shivakumar, Assistant Professor ISIR Mohali, who spoke on the topic of reactive intermediates, what can be learned from these unstable species, and Dr. Sumut from NTU Singapore, who has spoke on the topic of metallocycle catalyzed asymmetric PC bond formation reactions, and Dr. Gangadhar, who spoke on the topic of emerging contaminants, and finally, Dr. S. Anbu, University of Hull, UK, on the topic of basic chemistry of MRI contrast agents. And really, I thank all the speakers for accepting our invitation to deliver the lecture among us. Knowledge and positivity are the two things that increases on sharing. Yes, we get increased positivity on these 2 days because of knowledge sharing. I extend my sincere thanks to our head of the department, Professor Meenakshi Sundaram, for his support towards all our activities. And I thank all our department staff members for their support towards the success of this symposium. And I would like to thank all the participants from various institutions for their valuable presence in this 2 day symposium. In learning, you will teach, and in teaching, you will learn. Learning never exhausts the mind. Hope all get filled and enjoyed with the chemistry by our sessions. And I extend my thanks to my colleague and one of the co-convener, Dr. B. Arul Prakasham. And finally, my strong and deepest thanks to my host, Mr. Nirmal, for his untired technical support by hosting this session in the virtual medium. On this pandemic COVID world, consider chemistry among the most useful of science and big with the future discoveries. A lot of chemists working towards the invention of medicines for corona. Being a chemist, think like a proton and stay positive. Thank you, one and all. Thank you. Thanks a lot.
Thank you.
Yeah, Nirmal?
Yeah, yes.
Yeah, now you can conclude the session.
Thank you. Thanks everyone. I'm closing the Zoom now. Thank you.
Thank you. Thanks, one and all.